In this video, we're going to focus on the benefits of using our Optimizer Optimal to improve your road design workflow and the product that you produce. So with that being said, there's three big benefits that I'd like to cover today. One is going to be just how quick it is to produce a high quality design with the Optimizer. The other one's going to be how useful it is to minimize your earthworks and material movement to reduce construction costs. And then the third one is going to be using the Optimizer to standardize your design effort when comparing different options. So in the example we have today, I have two alignments. Both have been designed to a fairly high level. We've included our ground types. So this alignment has a fairly shallow rock layer for a good chunk of it on kind of this side of the channel. Both designs have a maximum grade of 18%, minimum K values of 3 and 4, and they start at the same place and end at the same place. So let's kind of start with one, and we'll talk about first what's driving the process in the Optimizer. So the operator for the Optimizer to work is minimize costs. So those costs are defined in our ground types. So here I've got my ground types. In this alignment I'm using 4 different ground types. So our ground types will carry geotechnical information with them, but they can also carry costing information. So here I'm telling it that gravel is going to cost me $12 a cubic meter to excavate, $4 a cubic meter to place and compact, whereas solid rock is going to be $48 a cubic meter and $4 a cubic meter to place and compact. So the handling costs can be unique for each ground type, and you can add as many ground types as you'd like, and they're user-defined values. Now, the other part of the cost equation is our material movement. So our material movement is broken down into free haul, overhaul, end haul. We define those based on hauling and loading costs. If we change those unit rates, it's going to change the breakdown for the optimal distance for the different categories of moving. So if it's going to cost us 20 cents to load free haul material, our free haul distance is going to be reduced. We'll just hit cancel and use the default values. So that's the relationship. Now in our settings here, just to get a comparison between the two, I've got pits defined, smart pits and smart waste sites. I've got a couple spots here where I'm using a stacked rock fill. So I've defined my fill material as being solid rock, which has a steeper fill. And then I've got my sub-horizons here. So we'll do our comparison of the two by hand designs. We'll click recalculate, recost, and I'm going to just recost both. So by hand, it'll take a moment to calculate. Our alignment 1, so this switchbacky alignment, is going to cost $624,000. I'll just pull that over so we can see the units are in thousands. This alignment, so fewer switchbacks, bit more rock, we're at $580,000. So that's our baseline. Both of these took me quite a while to design, so most of it took me a few hours to design them actually. But let's see if we can do that design a whole lot quicker. So we're going to use the same horizontal. We're just going to automate and optimize the generation of our vertical alignment. So I'm going to click over here, click new, vertical. So I'm doing new just so I can use this as use the old alignment as our baseline. I'm going to set my standards. So I want my grades, this fits in my case, and I'm going to use fast curves. So my minimum sag is going to be K value of 4, minimum crest is going to be a K value of 3. Yeah, and grades minus 12 to 18. Control points. In this case, I want to add a control point just at the start of my alignment. So we tie into the existing road that we're building off of. Other instances where you want to use this is if you have a major crossing. The software is looking to minimize earthworks costs. It won't consider your crossing parameters, so oftentimes you'll want to put a control point at a major crossing or something else where you want to fix the alignment to be at a certain elevation. I've also got our pits. So we've set that up before for use with the traditional design. These are smart pits, so it's going to figure out how much material to pull from for each example. Pull from or store material in. Unit costs is the same parameter that we've kind of introduced. And constraints, in this case I'm going to leave it unconstrained. I think I can move my material in both directions. So if we had a section where you could only move material backwards, we could account for that. And same with forwards. If we wanted to allow side cast of material, we absolutely could. So rather than hauling excess material to a spoil site, we could store it adjacent to the road. And then if we had any geometry parameters we wanted to account for that weren't control points, but say you had a section where you wanted to be in full bench, or a section where you wanted to overland and have a minimum fill depth, we can assign that. So that one's configured. We'll set as current. And we'll do our optimization. First thing it's going to do is go through and sample along the length of our road in order to make that optimization happen. And then it's going to solve. And in this case, it should solve fairly quickly. And we're going to end up with a fairly humpy bumpy road. It's going to be the cheapest option, but our curves are going to be butted right up against us. If we wanted to force tangents between our curves, we could change the setting. So we can see we have a lot more curves. We're also tracking the ground much better. So there's our original alignment versus the automated design. Pretty subtle differences, but they do add up. So with the original design, we're at 624. And we've dropped that down to 371. So definitely a significant savings by using the optimizer. It was also way quicker to optimize that than to design it by hand. We'll do the same for our other alignment here. And I'll also just mention something that I didn't explain at the first one. When I said it was going through and doing its sampling, on this general tab, I've told the software that it's going to sample along the length of my road in 25-meter intervals. And then in my vertical control, we're allowing the software to move that alignment up or down 10 meters relative to ground. So we're creating a potential band where the road profile can be placed. So this will use the same standards. Now in this one, there is a couple control points I'd like to add. So the control points I want to add in this case, this alignment crosses a couple crossings. So I want to add in a control point at the start of the alignment, same as the last one. And I want to add in a control point at station 1052.8. and I want that to be 1190.4. And I want to add in another control point at station 1970. And I want that to be at 1290. So before we optimize or change anything, I'll just touch on why I'm doing that. So here, is one of my control points. I'm crossing the top end of a fan. I want to have it so if I lose my crossing, I want it to funnel the flow over my road at that location. So I don't want to alter the fan. So that's just an example of where we'll use the optimizer, and the user will still have as much control as they want. Now the other control point I have is up here, and same thing. I just want my crossing location to be at a certain elevation. We've got our controls defined. Pits, same thing as before. Unit cost, same thing as before. And constraints, I will add a couple of constraints in here. And in this case, I just want to add it from station 1025 to 1105. And that's that same reason. That's where we're crossing the top end of the fan. And there. So I just don't want the center line to be in cut at all. And with that, I'll touch on these last two. So here, if we expected it to take a long time to run, we could reduce our stopping conditions from fully optimal, so most people don't. And then in our display, it's just whether we see the our original alignment versus the design alignment, or the optimized alignment. So we've got that set up. We'll just optimize it. And let's see how much we can save off this one. Here we are. So in this case, again, subtle changes in the alignment make a not as significant change in our design, but still considerable savings. We went from 580,000 to 466, and we saved design time. And with this, originally this was going to be the cheapest option if we just relied on our by hand design for what road gets built. Now we can see this one's 466 after we've optimized it, and this one's 371. So contrary to what we went into the process expecting, our switchback option, or more switchback option, is the cheapest solution. So those are the big benefits I wanted to touch on. One more benefit that I'll touch on is, I won't go into a lot of detail on it, is the optimizer is looking at the design in more detail than people will using traditional design methodologies. So with that, we've got those sections where I've assigned stacked rock fill. So here I've got my steeper fill slope angle. Now that's a different type of material. So rather than just the mass haul diagram, which is lumping everything in together, what we're using is the Optimal to solve for material movement. And what this is doing is we've got different materials and it's accounting for the balance of those different materials individually. So here our hard pan and fractured rock that we're generating is moved outside of that section, but we're not generating enough solid rock, and that is getting moved back to fill in that material. So we've got material moving in this direction and material moving in that direction. Oh, I meant to, yeah, sorry, that's where it was. Solid rock, hard pan going one way, and yeah, so our different materials are being balanced and going in the associated direction to account for all those complexities that are really hard to consider by hand. Thank you for your time.